This will be all you need to know in terms of differentiation and integration formulae. It makes much more sense to put them together and learn the connectivity between the two. So we're going to start by the function on the left column here, and then what do you get if you differentiate the function? So I write here differentiation, and then also what do you get if you integrate that function f(x). So here I write integration, and then maybe I can get some line here. Perhaps the most basic function to differentiate or integrate, and this is also perhaps the very first one that will be taught in any syllabus. So it is a polynomial function, which is x to the power of n, where n can be any number, positive or negative, a fraction, but there are some exceptions, which I'll tell you later. So if you differentiate x to the power of n, the most intuitive way to learn this is just to bring n down to multiply in front, and then we have power subtracted by 1. So that is n times x to the power of n minus 1. If you integrate x to the power of n, it is kind of like the reverse of differentiation. Instead of bringing n down first and subtract the power by 1, we add the power by 1 first and divide by n plus 1. Here I'm going to ignore the plus c constant for now because we only care about the formula here. Now what are the exceptions that I mentioned earlier? Well, for differentiation, n cannot be 0. For integration, n cannot be minus 1. The next one is still quite basic. It is just a constant. So a constant can be just any number that is not a variable. Because, as you may already know, differentiation is finding the rate of change. So being a constant implies that there is no change, hence the name. So when you are finding the rate of change of something that doesn't change, it should be 0. That means differentiating a constant should always be 0. However, that is not quite the same for integration, because actually we can apply the first rule up there. But let me simplify it for now. Integrating it, the result would just be putting one more variable to it. So in this case you get kx, just put one more x, simple. And there is no exception here, you get kx. Next, trigonometric function. So let's differentiate a sine x. Well, differentiate a sine x, we get a cosine x or cos x. However, integrating sine x, we get a minus cos x. So you see the connectivity there? That means you have to be careful because some people might get confused between the two. And you will now see why I put these together, because for cos x here as a function, when differentiated, we're going to get a minus sine x. And when we integrate a cos, we get a sine x. If you don't already know, differentiation and integration are reverse operations to each other. That means if you differentiate sine, you get cos. If you integrate cos, you get back to sine. If you differentiate cos, you get minus sine. So that means if you integrate minus sine, you get a cos. And that is why here, integrating sine, we have to put a minus sign in front of the cos. Now, however you would like to remember these, just know that there is some kind of opposite sense between differentiation and integration, and try not to confuse between them. Well, we are not forgetting the other trig function here, which is the tangent, or tan x. So if we differentiate tan x, amazingly we get a sec squared x. But the integration of tan x is less popular to remember. But I'm gonna write anyway. Integrating tan x, we get a ln sec x. Those of you who don't know what a ln is, this is natural log. Maybe don't be intrigued just yet, just get along with it. Now, we're not done with the trig function, because you should also know differentiate sec x. Sec is just the reciprocal of cos x. Differentiating sec x, we get sec x tan x. And again, the result of integrating sec x is not to intrigue you guys here, but I'm going to write anyway. It is ln modulus sec x plus tan x. Now the point here is that there is a pattern here for you to learn. If you've already learned the reciprocal trig functions, then the reciprocal of tan would be a cot x. So differentiating cot x would be similar to differentiating tan x. Instead of giving a sec squared, we instead have a cosec squared x with a minus sign. And if you've learned the three trig identities, you know what I mean here. Because sec and tan are in the same identity, cot and cosec are in the same identity. The extra thing here is just we have a minus sign. The integral of cot x is not quite relatable. It is ln of sine x. The other pattern that you will recognize here is that what do I get if I differentiate a cosec x? Differentiating sec x, we get a sec tan. Try guess here. If differentiating sec, we get sec tan. What is differentiating cosec here? Yes, you may have guessed it. We get a cosec x and cot x. You see, sec is kind of similar to cosec here. Tan is kind of like similar to cot. But we have a minus sign here as well. Now luckily, there is a pattern here that is similar to integrating sec x if we want to integrate cosec x, because integrating sec x gives you ln in modulus sec x plus tan x. If we integrate cosec x, we get ln in modulus cosec x plus cot x, again with a minus sign. So there is a pattern. Now when you use this table, always remember that the result of differentiation can be used to find the integral backwards. For example, if I differentiate tan x, I get sec squared x. But if I integrate sec squared x, I do get tan x. And this applies to every formula here. Now let's move on to a different kind of function. Let's do exponential this time, and this is perhaps the easiest to integrate or differentiate. So I have e to the power of x. Surprisingly, differentiating e to the power of x gives you e to the power of x. Better yet, integrating e to the power of x is also e to the power of x. So that's quite easy, right? However, e is an Euler number, which is about 2.7 something. What if the base of the index is not e? Let's say, what if it's a to the power of x? When you differentiate e to the power of x, you get the same thing. The base and the power stay the same. And there is some similarity here that we can use when we differentiate a to the power of x, which is, again, we get a to the power of x, but we need to multiply that by a natural log of a. And what about integration? If you integrate a to the power of x, you also get a to the power of x. Now, instead of multiplying, you divide by that ln a. You can see the pattern here that the division of the constant is not new, because we already have the division of n plus 1 here when we integrate a polynomial function. So as you can see, this is a similar behavior for you to observe so that you memorize it better. Next to exponential would be logarithmic function. So let's take ln x. Again, ln is just a short name of natural log. Some people call it ln or ln, but I call it ln. Differentiating ln x gives you 1 over x. Integrating ln x would require that you know a bit about integration by parts. So I'm not going to put it here just yet because it's perhaps not quite the formula you need to memorize, but it is something you need to learn later. So I think here we have completed our table. Now you may wonder, what if the argument is not x? For example, you may have sine of 2x or sine of kx, or you may have e to the power of something else that is not x. That is another whole video that I'm going to make. So make sure you subscribe and stay tuned. And don't forget, guys, keep studying.